My name is Keiji Ohnaka at the Universidad Andrés Bello in Santiago de Chile. I would like to present milli-arc second resolution imaging of the object called Toby-Jug Nebula. This is an optical image of the Toby-Jug Nebula. It's a beautiful bipolar nebula about 4 arc minutes across. This looks like a planetary nebula or protoplanetary nebula. However, its central star is still a red giant with a spectral type of M1 to M3. So this is a rare case in which a red giant central star has recently developed a prominent bipolar nebula and provides us with an excellent opportunity to study the bipolar nebula formation. That's why we carried out milli-arc second infrared interferometric imaging using the Very Large Telescope Interferometer. And we use the amber and gravity instrument operated in the 2 micron region, very qualitatively speaking. By combining 3 to 4 small telescopes, we can obtain the spatial resolution of a virtual 130-meter telescope, which is about a few milliarc seconds. This is the same optical image of the nebula. Now comes the image obtained with VLTI at 2.25 micron. So the field of view of this image is just 20 milliarc seconds. So the central part is very compact compared to the arc-minute scale nebula. What we see is the central star and an incomplete elliptical ring. This is the inner rim of an equatorial dust disk viewed from an intermediate inclination angle. And the size of the ring is 5.3 milliarc seconds times 3.5 milliarc seconds. And the star's angular radius is about 1.5 milliarc seconds. So the inner rim is quite close to the star, actually only 3.5 stellar radii away, or 2 astronomical units. We come back to this point later. We obtained images not only in the continuum but also in the sea of bandheads, as you can see here. And starting from the continuum image here, I'm going to show you the images in the sea of bandheads. Here, the central emission is more elongated in the north-south direction. Next bandhead. This is 13 CO, back to 12 CO. So the central emission is elongated in the north-south direction. This means the stellar atmosphere is more extended in the equatorial plane, or there might be a CO gas disk inside the dust cavity, but we cannot distinguish 2 possibilities at the moment. We also carried out 2D radiative transfer modeling to derive the disk properties. Here is the upshot of our modeling. As you can see, the SED is well reproduced from the optical to the mid-infrared. And here is the model image at 2.25 micron, which is in agreement with the observed image. We found out the disk is optically fixed and viewed from an inclination angle of 55 degrees. What's important is the predominance of large silicate grains as large as 4 micron. This means efficient grain growth in a stable dust disk. And usually, binarity is considered to be a key for the formation of bipolar nebulae. However, our VLTI images show that there seems to be little space for a companion in the dust cavity. Timmerwitz and Lubo shows that the tidal truncation radius is about 1.7 times the binary separation. But we observe that the inner rim is about 3.5 stellar radii. So by combining these two, we can say that the binary separation should be smaller than 2 stellar radii or 1.2 AU, which is quite close. And M giants have dense outer atmospheres extended to 2 stellar radii. So if a companion is orbiting through this dense atmosphere, it's probable that it simply spirals in to the red giant due to high friction. So this argument disfavors the presence of a companion. So what happened? Maybe Toby-Jug nebula and disk might have formed in violent binary interaction, maybe connected to the common envelope evolution, and companion might have been shredded. That's why we don't observe it, maybe. but we need imaging with a higher dynamic range to confirm this scenario.